This video will be a celebration of the birthdays of Paul Dirac and Roger Penrose, who were both born on August 8th. Due to audio recording delays, this will be uploaded on the 12th, which is the birthday of Erwin Schrödinger. We will be talking about the gamma function and its utilization in non-commutative geometry, specifically as how it's a generator of the moments of a cutoff function for the Seeley-DeWitt heat kernel expansion of the spectral action for non-commutative physics. We'll give a quick review of the spectral triple, which we have covered in the last few videos. Our spectral triple is given by an operator algebra A Hilbert space H, and the Dirac operator D. A is a tensor product space of all smooth infinitely differentiable functions on a Riemannian manifold M. In this case, it's a Lorentzian metric. And it is crossed with the finite extension algebra C plus H plus N sub 3C, where C are the complex numbers, H is a set of quaternions, and N sub 3C are all 3 by 3 complex matrices. H, our Hilbert space, is given by the function space of all square integrable functions, L2, of the manifold M with a spinor bubble assigned to it, S. And that is tensored with the fermionic degrees of freedom, which is a finite set of Hilbert spaces. D is our Dirac operator. We have the geometric part acting trivially on the algebra in the Hilbert space, so that's why it's tensored with 1. On the other hand, we have gamma sub 5, tensored with the internal degrees of freedom of the Dirac operator. This is to ensure chirality remains stable in our theory. We shall recall from the last presentation that the spectral action yielding our known physics can be expressed by the following. It will be this trace function that we are interested in. We will recall from the prior video that we focused on performing an asymptotic expansion of the trace term to yield gravity, gauge fields, and the Higgs field using the Seeley-DeWitt coefficients. In that video, we decided on n equals 4 because we were working with a 4-dimensional spacetime, and this yields the following asymptotic expansion in terms of the Seeley-DeWitt coefficients. We have a scaling function lambda to the power of 4 minus k. Remembering 4 was chosen for our dimension constant, so this normally would be lambda to the n minus k. A sub k of d squared, that's the Seeley-DeWitt coefficients acting on the squared Dirac operator, and f sub 4 minus k are the moments of a cutoff function. In the last presentation, I focused on the Seeley-DeWitt coefficients with that squared Dirac operator, and they correspond with the familiar action principles of our field theories. This time, however, we'll focus on the moments of the cutoff function f itself. F sub 4 minus k are, as I mentioned, the moments of our 4D space-time cutoff function. And that can be expressed as a special case of a Mellin transform. And so we have the Mellin transform in terms of f of u and 4 minus k, and that gives us an integral ranging from 0 to infinity of f of u times u to the 3 minus k, all integrated in respect to u. But now that we have this information, we can begin by expanding the series so we can see each term independently. But due to the fact that we're working in an even dimensional spacetime, alongside that squared Dirac operator, odd terms will automatically go to 0, leaving us only with even terms. We're going to leave the moments of the cutoff function definition in terms of the Mellin transform so that we can see what these terms correspond to on the top section for this trace function. To solve for the moments of the cutoff function, we must decide on a specific cutoff function f of u. A common choice that we use to handle our integration is an exponential function of the form e to the negative u. So now we have the Mellin transform of e to the negative u in 4 minus k. And so that gives us the integral from 0 to infinity of e to the negative u times u to the 3 minus k, all integrated in respect to u. This integral is easy to solve because it's just the definition of the gamma function, but it's evaluated at 4 minus k. This will imply the following. Since f sub 4 minus k is equal to gamma of 4 minus k, it follows that f sub k is equal to the gamma function of k. Our trace term can now be expressed in terms of this gamma function. We have gamma of 4 for our first term, and that corresponds to the cosmological constant term, yielding the volume of our manifold that happens to be expanding in reality. And then we have the gamma function of 2, and that corresponds to the scalar curvature, the Ricci scalar curvature, and when you integrate this over the space-time with square root of negative g, where g is the determinant of the metric tensor, you receive the Einstein field equations of general relativity. And so that corresponds to the Einstein-Hilbert action. Gamma of 0, however, is a divergent term. But for any non-zero positive integer n, the gamma function can be represented by this finite n minus 1 factorial. And so our first two terms here, the cosmological constant term and the Ricci curvature scalar sector, which gives us general relativity, these are already finite terms. Because gamma of 4 just equals 6, and gamma of 2 just equals 1. So this simplifies the first two terms as follows. So now that we have finite terms here in terms of a scaling function and the Seeley-DeWitt coefficients, let's focus now on that divergent term, a sub 4 d squared with the gamma of 0, which corresponds to Yang-Mills and Higgs terms. We have to get rid of the singularity, gamma of 0. To solve that problem, though, we can treat the singularity formed by the gamma function at 0 as a pole in a corresponding complex valued space. This gives us, however, an amazing result. We'll resolve the singularity by regularizing the gamma function evaluated at 0 using the Cauchy's residue theorem and Laurent series expansion. We first recall the definition of the gamma function evaluated at 4 minus k. To obtain gamma of 0, we simply set k equal to 4 in that equation. This is still also a divergent integral, so we need to find a way to turn this into a contour integral so that we have a way to handle the singularity that occurs. So we'll convert this to a contour integral over a complex manifold with a unique value s, and that gives the following. That gives us the contour integral, a closed contour integral that is, of the integrand e to the negative z times z to the negative s, and this is integrated in respect to the complex value z. We then perform a Laurent series expansion of the integrand around s equals 0 to yield the following. This gives us a divergent term 1 over s when s goes to 0, but this also gives us a minus the Euler-Mascheroni constant, or we should say the Euler-Mascheroni constant, if we will, plus the zeta function of 2 times s, plus the zeta function of 3 times s squared, plus the zeta function of 4 times s cubed, plus so on and so forth. And we will continue getting this pattern that for every s to the n, there is a corresponding zeta of n plus 1. The residue of the gamma function at s equals 0 is equal to 1. Our regularized term can be expressed as the gamma function minus the divergent part 1 over s as s goes to 0. We'll take all of the zeta terms corresponding to an s using big O notation, and we'll contain that in O of s. Since we are interested in the case where s goes to 0, as we've continued to say, our higher order terms O of s involving the Riemann zeta function disappear because anything multiplied by 0 is of course 0. And we can see the clear divergence then of 1 over s as s goes to 0, because that gives us essentially a divide by 0 concern. But when this divergence itself is subtracted from the gamma function, we obtain our regularization term for gamma of 0, yielding a single term Laurent polynomial. And that is just the negative Euler-Mascheroni constant. We'll recall the heat kernel expansion, that's important. And now we can replace gamma of 0 with the regularized gamma of 0, which is equal to the negative Euler-Mascheroni constant. We have now given finite value as a cutoff for the Higgs and the Yang-Mills fields. By choosing different cutoff functions, we didn't have to choose e to the negative u. We could have used another one. Heck, we could have even just used the number 1, and we would have gotten a slightly different result here. But by choosing these different cutoff functions, a similar procedure to what we have shown in this presentation can be performed using Euler's beta function, the Riemann zeta function, Dirichlet's eta function, polygamma functions, and more. Based on what behavior we're trying to look for in our integration and in our cutoff values, we can choose different things to correspond with different levels of simplicity. It should not be surprising, though, that we do obtain the Euler-Mascheroni constant in this way, however. Let's consider the digamma function, given by the following. So psi of x is the logarithmic derivative of the gamma function. And let's be careful when we're looking at this d by dx times the ln of gamma of x. Really what we're saying is that we're taking the regular derivative of the gamma function and then composing it with the quotient of the original gamma function. When x goes to 1, the denominator likewise becomes 1, as of course gamma of 1 equals 1. So we're left with a gamma function prime of x as x approaches 1. And that just gives us the negative Euler-Mascheroni constant. So that's super cool, but that's already kind of known. And so that's why it ends up actually working out so well for our Laurent series expansion. It has to do with harmonic series. So now let's talk about the spectral zeta function, which is more or less a generalization of the Riemann zeta function and a couple of other functions. So let's go back to that trace term, but this time we're just going to look at its actual closed term, the trace of f of d slash lambda. And by selecting our cutoff function to be e to the negative u, we end up getting the following. We're going to square operators because the Seeley-DeWitt coefficients a sub k operate on d squared. So when we use e to the negative u, we promote to the trace of e to the negative d squared slash lambda squared. By taking the trace over the spectrum of the Dirac operator, we obtain the spectral zeta function. We're going to show this spectral zeta function in terms of how we would normally write the original zeta function, but in this case, we are summing over the spectrum of the eigenvalues for the Dirac operator. And so that's a generalization of the Riemann zeta function. And the Riemann zeta function itself is actually just a special case of this specific sum where the eigenvalues of the Dirac operator are yielded by positive integers. And so then we can choose various types of eigenvalues. And we can form other zeta functions, Dedekind zeta functions, Hurwitz-Barnes zeta functions, etc. We can form the Dirichlet eta function and other forms of eta functions. We can form polylogarithm functions, the Lurch transcendent, theta functions, Bessel functions, Dirichlet L functions, Ramanujan's tau function, various levels of hypergeometric functions. We can even generalize the Euler-Mascheroni constant itself when we consider eigenvalues modulating around 1. And we can even write this as a Mellin-Barnes integral along a vertical contour, showing a generalization of Euler's beta function. Speaking of Mellin-Barnes integrals, check out this Kratos-Barnes transform. Thanks for watching.